Module 2.3, we're going to be talking about characteristics of attributes. So their name, type, classification, category, source, domain, value, optionality, and their role in the model. We're going to look at how attributes should be placed because there are data modeling and business implications to what entity an attribute is associated with. And we're going to look just a little bit at this idea of strong and weak entities. And so when we're done with module 2.3, we'll take a short break and then we'll come back to finish up for the night. So our entity, as we've discussed, this is a conceptual representation of some object of interest, some observed or unobservable reality. And really what an entity is a set of related attributes, okay? And they can be in relationships with other entities. Our instance is just a single occurrence of an entity type, so a specific horse that is a part of our horse entity. An entity class is this set of entity types that have shared properties, maybe strong or weak, yeah. And so entities are made up of attributes. So what is it that makes up an attribute, or how do we describe an attribute? And we can say an attribute has a name, so this is like color, or name, or sex, or weight, right? These are the names of our attributes. Attributes can have different data types, numeric, alphanumeric, and date time being kind of the big classifications, and there's a lot more specificity under that, but numeric, alphanumeric, date time, and binary blobs are kind of the main data types that we're looking at. Attributes can be either atomic or composite, and we're going to talk more about what all of these mean in just a couple of minutes. Single value or multi-value, real or derived. We've talked already about the implicit and explicit domains of attributes, their values, whether they're optional or mandatory, and whether they are key or non-key attributes. So as far as our attribute type goes, again, kind of the big categories here, we can have attributes that are numeric, meaning they are only numbers. There are no non-numeric characters in the values of these attributes. And this is primarily going to be when we want to do any kind of mathematical operations on the value of an attribute. Okay, so something like your salary is a really good thing to have as a numerical attribute, because then we can do something like give you a 10% raise, right? We can do math on that. On the other hand, something like your phone number, even though it's made up only of numbers, doesn't make much sense to store as a numeric value, because we would never do any math on your phone number, right? You would never add 10 to your phone number or take half of your phone number. Like, that just is a nonsensical thing to do. So typically, if we're not going to be doing math on it, if it's something like your phone number or your credit card number or a zip code or an area code, we just want to store those as alphanumeric or as character attributes, because then we can do all kinds of nice text formatting. So if we had all of our phone number, the numeric characters stored as an alphanumeric string, we can do character manipulation, like add a parentheses around the first 3 digits and put a dash in the middle. Okay, that's a lot harder to do if you've stored it as a numeric attribute, or at least you would have to convert it from a numeric to a string in order to do those types of string manipulations. So a little bit more flexibility in our alphanumeric attributes, which can be made up of any combination of letters and numbers. So things like an address, things like your name, all very good to store as alphanumeric. And then we have this other data type of date time, which really, I mean, this looks like we could store it as an alphanumeric string of characters, and you certainly could. However, if you want to do something like compare the difference between two dates, it's going to be a lot easier if you've stored this as a date time attribute in your database. Okay, and actually your database doesn't store your dates and times in a format that looks like this. It stores it using what we call the Unix epoch timestamp, which is the number of milliseconds that have occurred since January 1st, 1970, I believe is the particular date. So it's about a 12 or 13 character long number that changes every millisecond. So it changes 1,000 times a second. And that is generally how computers track dates and times. And if you wanted to say, how much time has elapsed between 8/29/97 and today, February 1st of 2021, the computer is actually going to be subtracting these two Unix epoch timestamps and then returning it back to you in some format that you can specify: number of minutes, number of hours, number of days, whatever floats your boat. So date time is a very special type of attribute in your database and gives you a lot more flexibility than just trying to store your dates as an alphanumeric string. And so within numeric, alphanumeric, and date time, different database management systems will have, typically, maybe a dozen different implementations of these attributes, depending on if you want an integer or a floating point or just a single binary bit, a 1 or a 0. So there's a lot of different options, and these vary from DBMS to DBMS. So we don't really go into a lot of specifics about these different data types, although we will be exploring that a little bit as we get into our SQL DDL code. But just know that kind of the big general data types: numeric, alphanumeric, date time, and then sometimes we'll see binary blobs of data as well. Our attribute classification, we can say attributes are either atomic or composite. And what that means, if it's atomic, that we cannot break it down into any smaller piece and it still be meaningful. Just like an atom is the smallest unit of an element that you can have, and it still remain that element. So for example, an attribute like last name is atomic, right? Because it doesn't make sense to take any smaller piece of this value. You can't break that down and it still be a meaningful thing, right? Just GRI is not meaningful in and of itself. Same for something like hair color or height, right? These are atomic values. A composite attribute we can break up into smaller things. And a good example of that would be something like address. So address, we could break up into smaller elements that still mean something, like your street number, your street name, your city, state, and zip code, right? And then at the bottom of these composite attributes are atomic attributes, right? Like zip code, we can't break up into anything smaller and it still be meaningful. The name of your street, we can't break up into anything smaller and it still be meaningful. But your address, we can, right? Your full name would be another example of an atomic attribute that's made up of your salutation, first name, middle name, and last name, right? Date of birth is a composite attribute that's made up of the month, the day, and the year you were born. But it doesn't make sense to break up your month of birth into something smaller. Like there is nothing smaller, right? Okay, so that's whether an attribute is atomic or composite. We can also say attributes can either have a single value or can have multiple values. So every employee or every student has one employee ID or student ID number, and that's it. You're going to have a single value for that attribute. On the other hand, if we're looking at something like skills or certifications, you might have many values for that one particular attribute. Okay, and we're going to find out a little bit later in the semester that there are special ways we have to deal with our data modeling for things like composite attributes and multi-value attributes, but we'll get to that in a couple of days. Okay, but just know that attributes can have either one single value or might have multiple values. We can say attributes are either stored or derived, and generally we want to store things that are not going to change, right? We're going to store things like your name. We're going to store things like your address and your phone number, things that are pretty static. But we want to derive things if they're going to be changing constantly, right? And a really good example of this is your age, right? We don't want to store your age in the database because what happens every year? Your age changes, right? And we don't want to have to go and update your age every year when predictably we know it's going to change every year. how could we derive your age from a stored value that is not going to change?
Date of birth.
Yeah, date of birth, right? Date of birth is our stored value, and then we derive your age by subtracting your date of birth from today's date, right? That's our derived attribute. We already talked a bit about our attribute domains. So we have explicit domains, things like spots, yes or no, sex, male or female, student type, freshman, sophomore, junior, senior, graduate, right? So these are some explicit domain constraints. Or we could have implicit domain constraints, like your age must be between 1 and 120, or your salary must be between 17,000 and 3 million, right? So those are implicit domain constraints, and also just whether we have to have a value for this attribute. Is it optional or is it mandatory is a domain constraint in and of itself. And then the final thing that we're going to use to describe our attributes are whether they have to be unique or not. Okay, so unique attributes are distinct for every instance in our entity. Okay, and this might be a single attribute or it might be a collection of attributes. We can have composite keys, but something like your employee ID, social security number, the ISBN, UPC codes, things like that are unique identifiers. And then within that, and we'll have more detail about this later in this semester, is the idea of key attributes and non-key attributes. So key attributes in and of themselves are not unique necessarily, but they are constituent components of our unique identifiers. Okay, so we'll have more detail about that a little bit later. So we have our unique identifiers, our key attributes, and then non-key attributes are any attributes that do not make up a unique identifier. So something like your classification, that you're a graduate student, that's probably not going to feed into any collection of attributes that uniquely identifies you, right? Your name, probably not. Your weight, your age, things like that, probably not part of your unique identifier. So all of these things we've been talking about are data integrity constraints, right? And these are the business rules that govern the behavior of our database, right? And our data integrity constraints are really just technical expressions of the business rules that we've defined by talking with our users. And we're going to preserve these across all three tiers, our conceptual, logical, and physical model. And we're going to, as much as we can, capture these in our entity relationship diagrams and the documents that go along with that. And we call those our semantic integrity constraint documents. So we're capturing our data integrity constraints and expressing those in our ERD and semantic integrity constraint document. Now, thinking more about attributes and entities, we have to consider what attributes together make up an entity. And sometimes it's very clear, right? So in this example that we're going to go through, we're looking at a relationship between a dormitory and a student, right? And a student can be assigned a room in a dorm, and there are some attributes that very clearly are attributes to describe a dormitory, right? The number of rooms, the name of the dorm, the type of the dorm, like whether it's a co-ed dorm or not, and whether it's for graduate students or underclassmen or whatever, right? So we have some attributes that are about the dorm, and some attributes that pretty clearly describe the student, like a student number and their name and their gender and things like that. But then what about rent, right? Is the rent that you pay for a dorm room an attribute of the dorm room itself, or is that an attribute of the student, or is it something else? And how we model that really changes what rent means, okay? So in this case, if we make rent an attribute of the room, then we're saying no matter who is staying in this room costs what it costs. It's always $500, right? No matter what. If we make rent an attribute of the student, then we're saying, all right, Tom is going to pay $1,000 a month for this room, no matter what room he's assigned to. which might or might not be correct. Or maybe it's something different. Maybe rent is an attribute of the relationship between the student and the dorm room. And the rent is going to vary based on both the student itself and the dorm room, right? So in this first scenario, we might say, all right, rent's an attribute of the dorm room. Room A costs $1,200 a semester because it's really nice. Room B is $1,000 a semester because it's just a normal room. And room C is $800 a semester because it's a small room in an older dorm or something like that, right? And no matter what student is staying there, this is how much each room costs. Perfectly reasonable approach. Or maybe we're in a situation where the university has a flat fee for all the dorm rooms, but we're going to subsidize how much each student pays based on like their scholarships or their financial need, or maybe they get a discount when they have good grades, something like that. So maybe one student pays $1,400 a semester no matter what room, another student pays $1,000 a semester no matter what room, and another student pays $600 a semester no matter what room. Okay, that's another approach, seems reasonable. Or maybe rent is an attribute of the relationship between the dorm room and the student. And the rent is going to vary based on what student and how nice the room they're in, right? So, if you're in a nicer room, you pay a little bit more, but you pay a little bit less for each room depending on your financial need or your scholarship or whatever other incentive program that the university has in place. So which of these is correct? How should we model this?
I think that's a business rule situation, depending
Absolutely.
on how the university functions, but I don't understand if it's a attribute of a relationship, what table does it go in? I can see dormitory and student being a table. I can't see occupies being a table. Is it a composite of this student gets a 10% discount of every dormitory? Is it in both? How do you put it in a relationship?
That is a really good question. Very very insightful. So to your first statement, you're absolutely right. It depends on the business rule, right? And all three of these are valid ways of doing it. Now, how do we do this? Like, what table is rent going to be in? And we're going to be going into a lot more detail about this, I think, next week. And if not, it's the next. But by using a special type of table we call the gerund to bridge the relationship between these two entities, we're able to have attributes of the relationship. So as far as the technical implementation on that, stay tuned, but there's going to be another table that sits in between these two tables in order to capture attributes like that. So great question and insight. So yeah, 3 good models. What we do depends on the business rules. No right or wrong answer here. So our final topic before we go into break is to discuss this idea of base or strong entities and weak entities. So our strong entities or our base entities are entities that exist independently of anything else that is happening in our database. Okay, so our base entities or our strong entities are going to have a unique identifier and are going to exist independent of any other entities in the database. A weak entity can only exist by being identified by a base or a strong entity. Okay, so weak entities don't in and of themselves have a unique identity. They are only uniquely identified when they are combined with the base entity or the strong entity that they are associated with. Okay, so weak entities are said to have an identifier that we call a partial key or a discriminator. Okay, so to give an example of this, let's imagine that we have these 2 entities that describe the buildings on campus and then all of our classrooms on campus. Okay, so in this case, building is a strong entity, right? We can identify every building independently of anything else. And we represent that by just having a box that is one solid line around it. Classrooms, however, we can't identify just a specific classroom. We have to identify that classroom in the context of what building it's located in. So classroom is going to be a weak entity, and we designate that by having this double box around classroom. And then here, instead of just a single line diamond, this double diamond indicates that this is an identifying relationship. And we have to have an identifying relationship between a strong entity and a weak entity. So here's some data to kind of show what's going on here. So we have building, that in this case, we're showing building name as our primary key that can uniquely identify every instance of a building. So we have Melcher, CBB, and SEMO, our 3 business school buildings here. And they have some other attributes like number of floors and the college they're associated with. But then we have classrooms that have a partial key, and we identify that with this dotted underline, that does not necessarily uniquely identify each classroom, right? Because all 3 of these buildings have a classroom number 110. So if I say we're going to meet in room 110, well, am I talking about this instance or am I talking about this instance? Or if I say we're going to meet in room 111, am I talking about this room 111 or this room 111? Okay, so classrooms cannot be uniquely identified unless we combine it with the building that that classroom is a part of. So if I say we're going to be meeting in Melcher 110, well, you know what classroom that is. But if I say we're going to be meeting in SEMO 110, well, you know what classroom that is. But 110 by itself, I bet almost every building on campus probably has a room 110, right? So 110 is not a unique identifier unless you pair it up with the unique identifier of the strong entity that identifies this weak entity, okay? So the double square indicates it's a weak entity. The double diamond indicates it is an identifying relationship, and the double square indicates it's a weak entity. So it's the attribute in the weak entity in conjunction with the unique identifier from the parent or the base or the strong entity in the identifying relationship. That's how you uniquely identify instances in our weak entity, by combining the partial key and the primary key from the strong entity that identifies it. So you need both the building name and the room number in this case. Now, this is there's many ways that we could model a relationship like this, and we might choose to do different things based on our business rules, performance considerations for the database, just kind of our own thought process and creativity in database design. And there's not necessarily one right or wrong answer. So there is both some science and some theory and rigor that goes behind database design, but there also is some creativity and kind of an artistic aspect to it as well. So, this is one approach to doing this design, and there are other approaches that would be equally valid. So, just something to kind of keep in mind as we progress through the semester.